As we've already talked about in class briefly, there's a special case of rotational dynamics where there really aren't any dynamics at all. In other words, the object which could be rotating is actually fixed in place, and we call this a state of rotational equilibrium. Many of you will go on to take a course that deals exclusively with this kind of situation. It's sometimes a course that's called statics. So examples of problems like this are ones found in some type of mechanical structure, such as you might have with a building or a bridge or a beam that's being supported with a cable. And it's really easy to analyze these kinds of systems using Newton's second law, both for translational motion and for rotational motion. The conditions are simple. For translational equilibrium, there can be no net acceleration, which means that the sum of all the forces that act on the object are equal to zero. Then, for the case of rotational equilibrium, the same kind of thing holds true, except it's the kinds of influences that would produce rotation that have to add up to zero. And we've already seen that rather than use force, torque is the quantity that's involved here. So when we add up all the forces and set them equal to zero along all the different coordinate directions that are possible in the problem, and we add up all the torques and set them equal to zero, we've got our conditions for rotational equilibrium. And in a particular problem, we usually know that the object is at rest, and we want to determine the forces that are required to keep it that way. One of the things that is important to remember as we analyze these types of problems, and you have several to do for your homework, is that when it comes time to calculate the torques and set them equal to zero, you're free to choose the axis of rotation wherever you want it to be. And some choices make the algebra much easier to do than others. Let's look at a specific example. So here is a rather simple example of a beam which is hinged on the bottom left-hand side, where that hinge is attached to a wall, and the beam is supported with a horizontal cable of length L, and then there's a mass M1 that's supported by a cable that hangs from the upper right-hand edge of the beam. The beam itself has a mass M2, and the length L is not the length of the cable, but it's rather the length of the beam. And then this mass M1 hangs straight down. The beam itself is at an angle theta with respect to the horizontal. So we know that this situation is in equilibrium, and what we want to find out the tension in each cable, and we also want to find out what the forces are at the hinge, because the forces at the hinge are important in order to be able to know what type of mechanical support needs to be provided there. So for the two objects that are here in the problem, the beam and then the hanging mass, we will draw force diagrams. So the beam itself, we redraw it over here on a separate diagram. It's important to draw the forces separately from the original picture, because otherwise the original picture gets too cluttered. So there's first the weight of the beam itself, which we always draw as being directed straight downward towards the earth from the center of mass of the beam. Then there's the tension T1 of the cable pulling down on the upper right hand side, the tension T2 of the horizontal cable, and finally there are the hinge forces, the forces at the hinge, which generally speaking will have both a y component and an x component. And rather than somehow try to figure out what direction the net force is in, the simplest way to analyze these problems is just to draw in F sub y and F sub x. Some textbooks call these H sub y and H sub x because they are the hinge forces. It's tempting to think that when the beam is oriented the way it is, that this net force would be directed along the direction of the beam. But it's not necessarily true. And so rather than assume that, it's better to simply write down these two components and then solve for them separately. So find the tension in each cable, T1 and T2, and the two forces at the hinge. So in addition to the beam, we also analyze the hanging mass M1, and that's rather simple. It's got the tension in the cable T1 and then its own weight m1g pulling downward. So right away we can see it's pretty obvious that T1 is equal to m1g in order for the mass m1 to be in equilibrium. So we've already got one of the tensions, which means there really are only three unknowns left in the problem: T2, Fy, and Fx. So we will now use Newton's second law to write down the conditions for equilibrium, but the question is, at what point should we choose to calculate the torques around? Where should we put the rotation axis? And we could put it at the bottom left-hand side of the beam, where the little hinge dot is, or we could put it at the center, or we could put it at the upper right-hand side, or anywhere in the problem, so long as we write down the condition that the sum of the torques is equal to 0. So I'll show how to solve this problem with a particular choice for the rotation axis that gives rise to the torque calculation in just a minute. Okay, so here is a redrawn sketch of the beam in this problem, and then the hanging mass, where all of the forces are indicated the way they were on the PowerPoint sketch. So remember, we're trying to find the two tensions, and we're trying to find the forces acting at the hinge, which have components Fy and Fx. And there was this mass, m2, hanging from the center of the beam. So I've drawn that downward force, m2g, hanging from the center. So it's clear right away that we can look at this hanging mass and see that adding up the forces in the y direction for this hanging mass and setting them equal to 0 gives us, in one easy step, the result that T1 is equal to m1g, right? Because we get T1, which is upward, so it's positive, minus m1g, which is downward, so it's negative. That's got to be equal to 0, and so T1 equals m1g. So we've already got one of the four quantities solved for, and this counts as a valid solution, right? Because m1 and m2 are given quantities in the problem statement. So the two masses, we know what those are. Alright, so we've got one part. Now we need to write down the sum of the forces in the x and y direction for the beam. Alright, so we took care of the hanging mass. Now the beam. So I'll write it down like this once again, and you have to be a little patient with me here because I left my stylus at home and I'm doing this from my office, so I'm doing this with a mouse rather than the stylus that I normally use, so it takes me a little bit more time to write these things out, and they don't look quite as neat. So in the x direction, the sum of the forces has to be 0, and likewise in the y direction. So we'll go ahead and write these down. And then, last but not least, we'll do the torque calculation. So in the x direction, it's pretty simple. We've only got two forces, right? So we've got that the hinge force, the x component of the force at the hinge, F sub x, minus T2, because that's the only other horizontal force in the problem, equals 0. And this doesn't really solve for either one of these. They're both unknowns. But what it does tell us is if we're able to solve for one of these unknowns in one of our other equations, then we've already gotten the other one as well. So if I can use the other information from the y component force equation or from the torque equation in order to find either Fx or T2, then I've got the other one as well. Alright, so this equation will be helpful later on. Now in the y direction, we've got, of course, the hinge force has a y component, and we've called that Fy in our diagram. So Fy, and then there's two downward forces, minus T1, okay, and then minus M2G. Those exhaust all of the vertical forces in the problem, and that's equal to 0. So that's an equation that's going to be helpful, but once again, it's got two unknowns in it. So I can't directly solve for either Fy or T1. So I'm left now turning to the torque equation, which is the new equation that we get when we deal with problems involving rotational equilibrium. And the torque, in a problem like this where the axis is fixed, the torque can either be clockwise or counterclockwise. But we first decide where we're going to take the rotation axis to be. And generally speaking, you want to put the rotation axis at a point where several forces act, because a force that's acting along a direction that passes through a rotation axis does not exert a torque about that axis. It just doesn't have any perpendicular distance. So in this problem, I think the two best choices would either be the bottom left or the top right side of the beam. And I'm going to choose the bottom left. So I will indicate in my sketch, and you always should do this so that whoever is trying to look at your work knows what you've done. You should always indicate where the rotation axis is. So I'll use the bottom left-hand corner for that. All right. Now remember that when you have a torque, you're always going to use this expression that a torque that a force produces about some kind of rotation axis is equal to the magnitude of the force times the perpendicular distance that that force is away from the axis. So let's look, for example, at T2. And I'm going to draw in a dotted line along the direction of that force. And then I'll realize that the perpendicular distance between the line of T2 and the rotation axis is this distance right here. And my sketch is going to get a little busy, but I have to indicate what that is. That will be the perpendicular distance for T2. So I'll call it R perpendicular 2. And one thing I forgot to draw in the sketch is the angle theta. This angle here that the beam makes with the horizontal distance is theta. So that R perpendicular 2 is the vertical side of a right triangle that is formed with theta as part of that triangle. We can do the same thing with T1, right? We can draw a dotted line down to here and see, the perpendicular distance between the line from T1 and the rotation axis is this arrow here, and I'll call it R perpendicular 1 because it's for the force T1. And then it would be too crazy for me to draw it in this sketch, but notice the force M2G, when it is extended downward, it also defines a perpendicular distance from that line to the rotation axis. And so we will be able to figure out what these different R perpendicular terms are by using just a little bit of trigonometry. So we'll start with T2. So we want T2 times this R perpendicular 2 distance, which is the side opposite the theta in the triangle, in the right triangle. Remember that the beam itself has a length L. And so R perpendicular 2, we'll just write some of this down here, R perp 2 is going to be L times the sine of theta, because L is the hypotenuse, theta is the angle that's indicated, and the side that we want is the side opposite the angle. That's R perpendicular 2. R perpendicular 1, if we look carefully at that, we see that R perpendicular 1 is here in the angle theta, here is in that triangle. R perpendicular 1 is the base, so R perpendicular 1 is the side adjacent to the angle. So R perp 1 is L cosine theta in the right triangle that it is a part of. And finally, R perpendicular for the center of mass, for M2G, which is the center, which is the weight of the beam itself. Right? So I'll just, what should I call that? I'll call it RW because it represents the R perpendicular W. It's the R perpendicular distance for the weight of the beam. And since the distance from one end to the center is L over 2, this distance that I want, the horizontal distance, will be L over 2 cosine theta. So we'll put that down, L over 2 cos theta. And with those individual perpendicular distances identified, now we are all set to write down the torque equation. And we will take the counterclockwise direction to be positive. So T2 will exert a torque about the axis that would be counterclockwise. T1 and M2G exert torques that would be clockwise, so they will become negative. So in the positive direction we have T2, our perp 2 we know is L sine theta. Alright, then we have to subtract T1 times L cosine theta. And then finally, we take the torque that's due to the weight, and that would be minus the weight is M2G, and the distance we wrote down as L over 2 cos theta. And the sum of all those torques has to be equal to 0 for rotational equilibrium to prevail. So what I will do with this is I will use it to solve for T2. I already know what T1 is. So in the next line, I will substitute in for T1. So this becomes, to move over to the left, give myself a little more room, T2L sine theta. And let me, since I'm going to be solving for T2, let me get this term all by itself on the left, and then the two other terms on the right-hand side of the equal sign will both be positive. So one of them will be T1 L cos theta, or M1G L cos theta. And the other one, clearly, is M2G L over 2 cos theta. So plus, M2G was already in there, L over 2 cosine theta. Now we can see that there's only one unknown in this equation, and that's T2. Notice also that the L term is present in all three terms. So if I divide both sides by L, L will cancel. It will factor out of all three of those terms and will cancel out. So to solve for T2, I just need to divide both sides by sine of theta. So I get T2 equals everything that's left here, which is, I'll pull a factor of G out, right? Because G is common to both of those terms on the right-hand side. So I have G times M1 cos theta plus half M2 cos theta. And I suppose I could have factored out the cosine theta term as well. I probably will do that in my very next step, because this is all divided by, whoops, I don't like that. Let's try that again. Divided by the sine of theta. And we know, if we factor out a cosine term, cosine over sine is 1 over the tangent, or it's the cotangent. So if I just want to make this a little more compact, I can make it G cotangent theta times the quantity M1 plus half M2. And what's nice about that, too, is I get rid of the term that was in the denominator, because we've used the fact that cosine over sine is just cotangent. So that gives us T2. We've used the expression for T1. That gives us T2. And notice, we already said from one of our earlier equations that whatever we got for T2 was also going to be the same as Fx. So that's Fx as well. So we've got 3 of the 4 terms. The only one left is the Fy term. And that is easy to get, because from this equation here, we can solve for Fy. It only depends on T1 and M2G. So Fy now is equal to T1 plus m2g. T1 we know is m1g, so it's simply m1g plus m2g. And with this, let's take a quick look at it. We're basically finished with the problem. Here is the hinge force in the y direction. The hinge force in the x direction happens to be the same as the tension T2, and that's here, and T1 we have up there. So let's just check units to make sure that all of these are actually legitimate forces. Fy is a mass times gravitational acceleration, that's a force. T1 is a mass times g, and then T2 and F sub x are both g times a mass times a cotangent, which doesn't have any units. So we've got our answer here. All of these have the right units, and it's a relatively simple kind of problem to solve. Probably the trickiest part, looking back on it, is the part here where we have to analyze the forces that produce torques and figure out from the geometry what the perpendicular distances are that go into the torque equation. So take a look at that, make sure you understand where those distances came from and how to get them using the information provided in the problem. Hopefully this will help you set up homework problems like this, and I will see you in class.